Hello, it's Duncan. I've been having a lot of fun recently generating multi-word anagrams. The first video of the series used TDD to get a working algorithm. The second looked at profiling to see how we could add micro-optimizations to speed things up. And the last episode I did some property-based tests to more rigorously check that it was actually working. It's still too slow though, so today we're going to look at the big picture, analysing how our code is working and using that to deliver some significant speed improvements. Not by making the same things faster, but by doing the slow things less. You've arrived just as I'm finishing a change to the anagram speed tests. What I've done is I've extracted the code that makes a report. I have parameterized it with a number of repetitions so that we can warm things up on a large number of repetitions on a short phrase, and then run it on refactoring 2 with a fewer number of repetitions with the hope the hotspot has had a chance to do its job. And also I'm putting the expected result count in here, and we're checking it down here. And that's a smoke test that the algorithm is still working if we've changed it. So if we run this, you see it takes a little time. And our baseline is currently 546 odd milliseconds in order to extract the 128,270 anagrams of refactoring 2. So I'll just commit that. And now let's go and have a look at our anagram algorithm. If you haven't seen the first optimization video, I'd certainly go and watch that first. But just as a reminder, we have a list of words that we filter, leaving just the words that could be made from the letters in our input. And then for each one of those, we work out what remaining letters are left. And if that's empty, then we have an anagram and we call this collector with it. And if it's not empty, we call process again with the remaining candidate words. And there's a little optimization here. Also, since the previous episode, I've made a little change in minus letters in, and that's here. And this manual array manipulation resulted in a tiny speed up compared to using filter. Let's run this in the profiler and see what we get. Before we go on, it's worth noting that the profiler has slowed things down a bit. That's 600 milliseconds as opposed to 550 odd. Let's go and see the results. This is our frame graph where the width of these bars corresponds to the amount of time spent. And here, minus letters in, and so on. We can see minus letters in used quite a bit. If we select that and look in the method list, you can see that of the code that we've written, we do spend most of our time in minus letters in. The problem is that it's about as optimized as we can make it at the moment. We've made this run as fast as we can. So if we can't micro-optimize this anymore, what major optimizations could we be making? In order to give us some ideas, I'm going to instrument this process function. And in particular, I want to instrument how often we're calling minus letters in and with what inputs. To record that, I'm going to create a data class. I think we'll call it minus letters in invocation. And this is going to remember the receiver as our word info and the parameter, which is also word info. That's a vowel, and this is a data class. And now word info is private inside us. I think we might make that internal to solve that problem. And this could be an internal data class. Armed with that, our instrumentation is going to be a function that takes one of our minus letters invocations and returns nothing, just does something with it. And by default, we'll say that's an empty lambda so that we do nothing. And now in here, we can say go to our instrumentation, create a minus letters in invocation with the input, which is the thing we're about to pass to minus letters in, and the word info. We could push that down into this function here, but it's probably a little cleaner to leave it up in the top level. And now we need to pass that instrumentation down also into our recursive call, the same instrumentation as we were given. All right, I'm going to run the test with this no-op instrumentation just to check that it doesn't make them dramatically slower. Well, that's the same sort of speed as the previous unprofiled run, so it looks like it's relatively harmless, and that's important because you'd like to be able to leave this code in here for future experimentation. Right, let's go up the stack and allow callers of anagrams 4 to specify some instrumentation. So put these on separate lines. We'll take one of these and put it in there. And now as this is part of the public interface, we have a bit more of a problem. I think this may be a place where making this internal and having another version without that parameter that's public might be our best bet. Do this, take that out of there, this dot anagrams for input and depth. And now our internal testing code can use the instrumentation, but our public interface doesn't have it. Okay, run the tests again. This Stack Overflow error means I think we've confused things with this default value, so let's take that out. And we need to feed this instrumentation into our process. This now needs to specify the empty lambda. Try again. You may be able to hear our fans humming, but we're running at about the same sort of speed. I'll try one more and we'll call that a new baseline. So that's about 5.5 seconds. Now, what are we going to do with that? Well, let's go to our anagram speed tests. Move them over here, and we'll have an instrumented version of anagrams for refactoring 2. Instrumented. Now, we don't need lots of repetitions, so let's strip this back to the basics. We're going to call words anagrams for input, where that is my refactoring 2, and we're going to pass it some instrumentation. And what we're going to do is just going to remember every call. So we'll set up a mutable list. That's going to take minus letters in invocations. And every time we're called in here, we're going to say invocations add it. And we need to tell it that this is our instrumentation. In fact, we can throw away the results. We know what they are from other tests and focus on our invocations. Now, I've been thinking about this, and I think what I'm interested in is the number of letters in both the words, in the receiver and the parameter to our without letters in. And the reason for that, if we look down here, is that this algorithm is scanning through each letter in each word. For this word, it's scanning through each letter here and finding the index of where we're going through each letter in our receiver, once for every letter in our word, although if it finds it, it will bail early. So this is going to be more expensive for longer input words. Let's have a look at the size of those input words. And I'm going to do that by taking my invocations and mapping it. Each one of these is an invocation. And I want to extract the receiver's words length and also the parameter's words length. Now that will give me a list of pairs, and I'm going to group those by the pair. What's the type of this? Let's have a look. Well, it's a map of pair of int and int to list of pair of int and int. This will be the length of the receiver and the length of the parameter. And this will be all the invocations of those. What we want to do is count the length of this list once we group them, because that will be the number of invocations that have that receiver length and that parameter length. So now we want to map the values with it dot value dot size. And that will give us a map of pair of int and int to an int. And in that map, these are the length of the parameters, and this is the number of invocations with that parameter. So we can take that thing, conveniently called thing, and for each, we can take the entry and the count, and we can print the entry first, which is the size of the receiver, the entry second, which is the size of the parameter, and the count, which is the number of invocations. Let's run that and see what we get. So here are the results, and I think what they show is that there are 3 invocations of taking a 1-letter word out of a 13-letter word, and 249 invocations of taking 4 letters out of a 12-letter word, and so on. I think a picture may be worth 1,000 words here, so I'm going to take this data and put it into Excel. So let's paste, and you can see Excel has split on the comma to give us different columns. Now let's insert a chart, and that is the sort of thing that looks useful. Okay, in this chart, the area of each one of these bubbles is the number of invocations, and we can hover over it. So we can see here that 1114, which is subtracting 4 letters from an 11-letter word, had 1,808 invocations. And in fact, just hidden in here somewhere, we can just about find, maybe if we hover, we might be able to find that top point there, the 13.1. But I can't. You see some other ones here though. That's 13.3, that's 13.4, and so on. We can make things a bit better by scaling to 50%. That makes our smaller things disappear even more, but you can see here that most of our invocations are sort of squarely in the middle. We have 5.3 at 182,000 invocations. So after a little bit of tidying, we had the receiver length, the parameter length, and the count, and that produces this chart where each one of these bubbles, the area represents how many times we've been called with those two lengths. Now, given that subtracting letters from a word is going to depend on the length of both of those words, what we'd like to do is move these invocations down towards small words, down here. We'd like more small ones and fewer big ones. How can we do that? Well, I've tried a few things and one has stuck. And that is to take our input and sort it so that the long words are first. So input long words first. That's this, sorted by descending it.length. And now we can take that in here as our new input. Let's run all the anagram speed tests and see whether that has an effect. Well, now that speed is now 378 from our 550 or so. So really quite a bit quicker. And let's go and plot these points. Here then is the visualization when we pre-sort. If you compare that to the previous version, the unsorted version, you can see the center of mass of our invocations has moved down to the left, which means that we're making more calls to extract shorter words from shorter words, which is quicker. Here you can see our center of mass is around, say, 4.2, whereas in this case, our center of mass is up around 5.3. The total number of invocations here is 169,371, and here is also 169,371. So we haven't actually changed the number of times we've invoked the function. We're just invoking the function on shorter inputs, which is quicker overall. And that's really good for us. Right, that looks like a good place to check in. Before we do, let's just run all the tests. Okay then, all of our anagram property tests pass and our speed tests, but our anagram tests are failing. Let's have a look. And here we can see that now we've sorted by length, we're getting at the longest first word first. So actor is coming out first, and then a act, we're getting act first. This is the result of this sorted by descending. So let's go and fix this one. So let's pull that out as expected, and we know now that that is going to be actor, act, act A, and cat A. And actually that may be a nicer output order for us. Anagrams for refactoring 2, let's have a look at that. And again here, instead of getting the anagrams beginning with the first word alphabetically in our dictionary, we are getting the longest word in our dictionary that we can extract. So that's good and okay, providing it's the same size in total, and they are both 128,270 lines long. Okay, so we can approve that and run again, and now everything passes. And we can check in with add instrumentation and pre-sort words by size. There's a T in instrumentation, and we're done. Good. Okay, so back in our speed tests, I think we are now 35% faster than we were when we started. So it feels like we should be able to do refactoring to Kotlin now, right? I'm going to take this and say this is refactoring to Kotlin, and we say refactoring to Kotlin, and I'm going to cut down the number of repetitions. And I don't know what the expected result count is. I'll add a couple of zeros, and we'll find out what the actual value is by failing the tests. So let's run that. Okay, well that's 2 minutes later, it's still running. So that's no good. Let's stop it. Let's just do one iteration. and see how we do. Well, no, totally bored with that too. Let's stop. It certainly seems our time isn't scaling with the size of our input. So let's investigate that. What I'm going to do is I'm going to put in the intermediate data point. So there is refactoring t. Refactoring t has one more letter than refactoring and one fewer than refactoring 2 because we delete the spaces. So we should be able to do that. And then let's go refactoring to k. I'm going to cut down the number of iterations. Just go for 1 for now because you don't really need time resolution. And maybe another one of refactoring to co. Now I'm going to delete this one and now fold this away as we're not using it. And inside here, we will put in our input so we know which one's which. And I think I'm going to stop asserting the number because I know we're just guessing. Let's run that and see what we get. Now I'm going to use this output to populate a Google Sheet over there. So I think if we take that and select all those, then move right a word, another, and then back, copy those, we can put them in here, and then back, and select the beginning, copy that, and put it in here. Fill down the number of letters. And now let's graph the number of letters against how long it's taking us. Take this and insert a chart. And you can see here just how non-linear that is. In fact, it's looking pretty exponential, isn't it? Let's go and get some more data. Okay, so I've added some more letters and run that. Let's go and put these into our spreadsheet. And having put those results in, it really is looking like an exponential. One thing we can do is we can take the axis and plot it on a logarithmic scale. And if we do, you see it's a pretty straight line. The outlier will be the first one we run because that's warming everything up. In terms of time then, our algorithm appears to be in big O notation, O of some constant to the power n. Now there are algorithms that are worse than this, but really not many. So the question is there any clever hack we can make to change this from order of c to the n to something better, maybe order of n squared or something? Now one way to find out if there's hope is to look at the size of the output. If we're taking order of c to the n time, but our output is only growing with n squared or something, then we may be able to find a way to make those two match. So let's have a look at the output size. If I go to our reporting function here, then we've got these time and result counts, and my result count will be the time and result counts. They all should be the same, so I can pick the first, and then the result count is the first of those. I'm going to add that at the end of this report with result count, and we'll run all our tests again. Those are some pretty big numbers already. Let's go and put them in the spreadsheet. So we've taken that data, put it in here, plotted it on the chart, and again with the log scale you can see that the output size is a little bit more lumpy, but still as we plotted it on a log scale and it's linear, I think we'd say that is exponential as well. Now my logic goes that if our output size is order of c to the n, then that's a complexity I don't think we can beat. We can reduce how long things take, but every time we add a letter, we're going to scale exponentially. So we cannot change the laws of physics. We can make things faster, but we can't change the fact that it will get slower very quickly as we add letters to our input. A really promising idea for cutting down the amount of work we have to do was suggested by Pavlo in the comments to the previous video. His idea is that we look at the words that are anagrams for each other, like actioner and creation and reaction. Once we know that actioner is part of a valid anagram, then we also know that creation is part of a valid anagram. And also subtracting the letters in actioner is the same as subtracting the letters in creation and reaction. So we don't have to keep on doing that work. We can cut down the amount of work we have to do. Let's look at implementing that idea. One way of thinking about this insight is that at the moment we iterate through a list of word infos. And each time one of those word infos is a single word, and we represent that as a letter bit set. But if each word info was every word that shared the same letters, it would have a list of words. And every time we eliminated one of those words, we'd eliminate all of them. And every time we subtracted the letters from one of those words, we'd subtract the letters from all of them. So we could collect together lists of words that made valid anagrams, and then find the permutations of those lists, and that would be all of our anagrams. So to prepare for that, I'm going to give word info a list of words rather than just a word. So I'm going to make this words that takes a list of string, but I'm going to give it back a property, for now at least, of word, which is the first word. And it would be an error to build this on an empty list. Given that, then, we can populate with list of word here. And that compiles and runs fine. Now back up here in process, at the moment, our prefix is a string and our collector takes a string. And we add the words we found onto the end of this string with this prefix here. What we're going to end up collecting, though, are sets of words. So let's sort of back our way into that. What we'll do is we'll say that our collector is going to take a list of string, and our prefix will also be a list of string. And the list equivalent to the empty string is empty list. Now here, in our collector, we can take our prefix and just add on our word. And in fact, it's our word info word. We'll come to that in a minute. And the same here, where we're passing a prefix down into our recursive calls. This is prefix plus word info word. Take that blank line out. And now up here, this it is our words. If we look at the type of that, it's a list of string. So now we need to take that list of string and join them together with our space. So what we were doing is we were joining the strings together with spaces here with string concatenation. And now we've got a list of string and we're joining them together when we're done up here. Let's just check that passes the tests. Well, it does, so that's good. Now that we don't want to be collecting individual strings, we want to be collecting sets of strings, but those sets of strings are going to be our word info. So if we change this to word info, and this to the prefix being list of word info, then in here, we don't have to take the word info word, we can just take a word info and add it to the list before we pass it down or out. And then in here, we want to take the word out of the word info before we join it to string in our current implementation. And there is a transform and join to string, so we can say it dot word. And if we run that, we're good. But all we've done at the moment is move around the processing. Each one of these word infos has a list of a single word in it. So it will in fact be slightly slower than the previous code. Now how will we build these word infos that contain all of the words? Well, the answer is we'll go to our input longest words first. We'll group that by something that collects all words of the same anagram together. That is to say, the same individual anagram. And we know how to do that from a while back. What we can do is we can take the word, we can take its character array, we can sort those characters. In fact, we want sorted array, otherwise we get list, and then we can create a string out of all that. And these are groups, and if we look at the type of that, it's a map of the string, which is all the letters in alphabetical order, to all of the words that had that signature. They're all the words that are anagrams of each other. So now we can take this, go through all the values, and map those to word infos, if we had a constructor that takes the list of words. Well, we don't yet, so let's go and add that. A secondary constructor that takes the list of words, which is the list of string, and that will call the primary constructor with the words, and all of those words, the letter bit set will be the same, so we can just take the first one like that. And now if we go back up and look at the type of this again, it's now a list of word infos where the word infos will be all the words that have the same letters. Okay, we can't use that yet though, because if we were to put this into here, we'd only be pulling out a single word when we collect everything together. What we need to do now is find out the permutations we can get from a list of word infos. And for that, I think I'm going to write a test. What I've done is I've created a separate anagram implementation test, and these have all the little details that we're testing, the bits of the internal functions. Whereas anagram test is actually now a functional test. It checks that the whole algorithm works. So coming in here, we can write ourselves, That is one of the old ones. Let's get rid of that. So we can write a test for word info permutations. So now we're going to start with the list of word infos. So we'll call this input. And let's start with one word info that takes a list of, and we know these are going to be individual anagrams of each other. So let's use act and cat. What do we expect when we find the permutations of a list of a single item? Well, I expect to find a list of act and cat. So at simplest then we can say assert equals expected is our input permutations. And this doesn't exist, so we will create it in here. On list, it's going to return a list of string, and it's going to take a list of word info, making this E redundant. Now I can make that pass right now by saying return this first, words. So let's do that and run these tests. Okay, good. Now at this stage I always like to make sure that I'm working with pathological cases. So let's just inline that and that, lay that out, and then we will duplicate the whole test with empty. And the first case is that if we have an empty list of word infos and we get the permutations on it, then we expect to get an empty list out. And likewise, if we have a word info with an empty list inside it, that should also give us an empty list. I think that will fail. We'll run. And it does. So let's fix up here. And we can say, if this is empty, return empty list. And let's check that. And now we're still failing on the second case. But that's failing when we create a word info. And in fact, we know this is an invalid state. And for this sort of code, I don't mind just throwing an exception there. So let's remove that test and not worry about it. Okay, what now when we have a list of more than one word info? Let's duplicate this, and we'll call this maybe single word info permutations, whereas this one, we're now going to give two word infos. I think maybe we will give this tab and bat. So what do we expect to get out? These are permutations. So the first list will be act and then tab, and then act and bat, and then cat and tab, and then cat and bat. Really don't expect to see this pass, but we'll run it just to see. And it fails as we expect because we're only looking at the first item in this list. Now I'm going to turn this on its head a bit. What I'm going to do is I'm going to say I've got some sort of collector, which is a mutable list of string. And that's what we're going to return at the end here. But we'll return it as an immutable list. And that means that in here, we can say, if this is empty, do nothing, else take this first words and add them to the collector. That can go, that can go. And we'll just run that to see that it works in the cases where the previous one did. Okay, now I'm going to pull this out into its own function. And we'll call this permute into. And permute into is going to be the thing that calls itself recursively. So we're going to give it a prefix, string, and it's going to do much the same thing as the code in our anagrams. To simplify, we're going to say, if this is empty, just return. Don't add anything else to our collector. If this size is 1, then we need to go through all of its words, which is this dot first words, and add them to the collector. And we use the string concatenation we used previously, so this is my prefix and my word, where the word is here. And now if my size is greater than 1, and that would just be else in here, then I need to iterate over all my words, pass them recursively down into permute into, cutting off the first element with the one we just processed. So that will be this dot sublist from 1 to this dot size, permute into my collector, where my prefix is this prefix word. Let's see how that goes. Let's have a look at our failure. So it looks like we're there, but we've just got a prefix space here. And we had that problem before. It's because when our prefix is an empty string, we still put this space in. And we can solve it by saying substring 1. Just find out. Okay, that passes. I'm not going to say it was obvious. To be honest with you, it took me quite a time to work out, and I'm still not sure I like the way it's cast. But what we can say is we can say else, and then we can say this is this dot size equals 0, and we can make this unit but do nothing, and then this becomes a when. So now you can see when I've got nothing, I do nothing, after which when we've got one word info, we take each of its words and use them with a prefix and add them to the collector. And when we've got more than one, we take our first one and we recursively call ourselves. Run one more time with feeling. Good. Just check we work with another case. So we'll duplicate that. Let's put one in the middle with only one in it as a sort of sanity check. So we can put in A, in which case we expect act A tab, act A bat, cat A tab, and cat A bat. Is that true? Why, yes it is. Okay, now we're armed with this permute into. We'll take it, make it internal, and move it into our anagram code. I'll put it down here. And then up the top of here, we can use that in our collector. So now what we're going to do is we're going to take our groups and put them as our input, which compiles. And our collector, well, that now takes the word info, and what it's going to do is it's going to ask these word infos to permute themselves into our result. Well, that compiles. The question is, does it pass the tests? I'll run them all, and we'll see what we get. Now that may look disastrous, but just before we give up hope, let's have a look at this and see that our speed test for refactoring 2 failed because we had too many results, but it got too many results in 225 milliseconds. That was compared to our 350 milliseconds before. So we're generating more results, but in a much quicker time. Of course, we can generate the wrong results as quickly as we like. So let's see if we can work out what the problem is. Our property test here of anagrams are unique is probably a good one to look at. Let's go down and we can see here sac anus has failed, but 68 and 70 isn't a very useful diagnostic. You can see here we're saying they're unique by just seeing whether the set of anagrams size is the same as the anagram size. Let's get some better diagnostics out of that by taking this thing and this thing, and instead of testing the size, we'll join these to a string with a carriage return so we can see what we have. Okay, let's run just that test, see what we get. And now if you look at the difference for one that fails, you'll see that we have a duplicate of I melt no on, and a duplicate of elm it no on, and so on. So how are these happening? We can see this is happening because we've got two word infos, both of which with no and on. Previously in our process method, we were removing words we'd already considered from later iterations, but we're not doing that within our permutations. In fact, the difference between permutations and combinations is that in permutations, position matters. And so we couldn't call it permutation and get rid of those. We can fix things up in here for now. What we'll do is we'll create ourselves a little temporary buffer, which is my mutable list of string. Permute into that, and then we'll take that and remove the duplicates from it. So that's going to be map it to the word, split on a space, sort those alphabetically, join them back to a string with the space, and set those. And then that thing is the thing that we're going to take and add to our result. They all now pass. Our speed tests. Well, our speed test now will pass, and you can see that our normal one here is now 268, which was 350, so that's good. These are really rather slow. Let's compare those with our previous results. So here I've added the new results to our previous chart, and you can see there's this crossover here where our new results are slower until we get past 12 letters, at which point they become about twice as quick. So all the work we're doing up front to group the words that are anagrams of each other is taking time that's proportional to the size of the word set rather than the input letters. So that's a constant that pulls these times up, but pays dividends later on with bigger words. Now I'll run the instrumented test, the one that sees how many times we call minus letters in, and then take these numbers and put them into Excel. Then this is the visualization with our grouping. Now if we compare that to the sorted version, you see there doesn't appear to be much difference. But crucially, if we look at the total number of calls, it's 451,000 in the grouped case, and in the plain old sorted case, it was 1.7 million. So we've hugely cut down the amount of work we're having to do. And then finally, our acceptance tests, run those. And they are now failing because our output is in a different order. We could keep these passing by sorting the output, but it doesn't really do any harm to change it for now. And for the refactoring too, I will check that we had the same number of results. This differs because now we're sorting out batches of words alphabetically. But if we go down the bottom, we find they both had the same number of words. What order we'd like the words out in is a bit moot. I think I do, if anything, prefer the left-hand side one. So at some point I think I may sort by length and then alphabetically. But I think for now we're done by approving this and then running all of our tests. Well, there we are, all tests pass and roughly twice as fast for big inputs, but still unfortunately scaling exponentially with the size of our input phrase. Before we go, I'd like to say a huge thanks to Pavlo for his work. He has other optimizations I haven't shown here, and I'll link to those in the show notes below. I hope you've enjoyed this. I certainly learned a lot about analysing algorithms making it. If you did, then please subscribe to the channel, and consider buying the book that I wrote in that price called Java to Kotlin, a Refactoring Guidebook. Thanks for watching.